So I will switch from structural fatigue to functional fatigue. I will talk about the work we have done on capital nickel micropilars. We have applied some mechanical cycling, and I will talk more about functional stability of this material. The work has been done at the University of the Basque Country in Bilbao. The outline is the following. Initially, I give you a short introduction and motivation of this work. Then I will speak about the material we have used and the milling of the pilars by Fokusai bin. Then I will introduce the equipment we have used for nano-indentation, and I will present some reason about the particular behavior of the pilars on nano-mechanical cycling. And I will also talk about the damping capacity of these pilars, and then I will summarize some words about the functional stability of this material. So, as we all know, shape memory alloy experience this magnetic transformation, which provide this super elastic effect and the shape memory effect, and this is why they were quite used in many applications. And as smart materials, they become very important or very attractive when you decrease the size of the device you want to use, because of one main reason, which is the maximum work output you can get per unit volume among different smart materials, which is about 10 to the 7 joules per cubic meter. And in the past, there was a lot of attempt to use the most widespread shape memory alloy, nickel titanium, in this field, including in thin films. But due to some plastic deformation, this material could not be used at a very small scale. And on the other hand, copper aluminum nickel shape memory alloy have shown excellent functional properties at micro and nano scale. There were already some work published in the past. And of course, if one wants to use this material in real application, one has to look for the functional stability of these materials, for example, in damping application, but you have to go more than 1,000 cycles. Of course, this in comparison with fatigue studies not too much, but at least it will be a starting point. So the idea was to study the functional stability of copper, aluminum, nickel upon long-term mechanical cycling, to have at least small statistics about these properties. We have prepared several arrays of pilars, and then in particular we have studied the damping capacity of this material. The material we have used is the copper 14 weight % aluminium and 4% nickel shape memory alloy, which was homogenized in standard treatment for half an hour and then ice quench. The transformation temperatures as determined by DSC are the following. Mainly they are in austenite state in room temperature. We have used oriented single crystal with the O1 direction upwards. And to mill the pilars, we have used an FEI Helios NanoLab with the 3D nano prototyping software to produce a range of pilars. We produce different arrays of pilars, and I will talk only about one array of pilar we have milled, which is shown in this image here. This is magnification of part of this array, and as you can see, the section is square, but we also milled some pilars with a circular section, and although it is very tiny, there is a certain taper. That means that the faces of the pilar are not exactly perpendicular to the surface of the single crystal. And this is how this array of pilar look like when you look at it in the nano-indentor, using it as an AFM machine in contact mode. And so this is how it looks like when you look at in the nano-indentor, which is the main part of the main equipment for this study. This is a high-strength indentor TI-950. The main part of this equipment for the nano-compression test is the transductor and the piezo scanner, which is is here for small loads, and this is the other one for a little larger loads. Schematically is shown here. We apply the compression load here at the tip of this indentor, which is, in this case, spheroconical diamond indentor. And so, let's move to the result. Before we show you the very new result, I will summarize more or less some previous results we have obtained. In 2012, Professor Juan showed that after 100 cycles, an individual pilar had a very good reproducibility, a complete shape recovery, and a quite fast response. Afterwards, we went further up to 1,000 cycles, and again, it has been seen that the properties were maintained. But of course, we need to go further and to have some statistics, and that's why we prepared this arrays and we studied that in detail. In this slide, I show you the superelastic cycle for all the 16 pilars have been milled in this array, and in general, we can say that qualitatively the behavior is similar, but of course there are some differences from one to the other. First of all, the critical stress for inducing Mertens transformation varies from one pilar to the other. The cycles are not completely the same qualitatively, so each pilar has an individual behavior or some uniqueness. But if you cycle the pilar, what we have observed is that more or less the behavior is maintained. And here I show you the behavior of 3 different pilars. And initially what we observe is that there is a certain, after some cycles, there is a certain training. That means that we introduce some defects which get stabilized after a certain number of cycles. And then the situation gets more or less stabilized, and this is repeated for different pilars. I show you here only 3, but it is repeated in several of them. And after 200 cycles, it is observed that statistically, although the statistic is not so large, they seem to have a similar behavior. And since damping capacity was claimed as one of the potential application of this type of material, we studied the loss factor, which is defined according to this equation. Basically, this is the area of the cycle over the total area times P. And we determined this loss factor for the 16 pilars after the first cycles. And first of all, I have to mention that point out that the loss factor for metallic materials in this case is quite high. It's very good damping capacity. And this is for the first cycles. If we pass to the 200 cycles, it is observed that on average the damping capacity is maintained, and although in some cases, for example pilar 11, 12, 6, due to some stabilization of the martensite, we could not further have the superelastic defect. But anyway, on average, we could say that we have quite good and reproducible damping. But of course, 200 cycles is not too much, so we wanted to go further, and in 4 pilars we were able to go to 5,000 cycles, and as you can see in this image here, again after the initial training, the situation gets stabilized, and we have a quite good damping capacity, or quite good superelastic cycle after 5,000 cycles. Of course, 5,000 cycles in fatigue studies not too much, but you have to keep in mind that we are in a non-indentor, it's not a fatigue machine. And we also work on load mode. I would say that if we deform, if we work in displacement mode, and we introduce a strain which is 1% or 2%, we could go to much larger number of cycles. And about damping capacity, which is in fact the same type of data, after the initial training we get a plateau in the loss factor value, and which is quite reproducible after. And this is repeated not only for this pilot but for other pilots as well. So let me come to the conclusion, which more or less are already mentioned, but we think that with this result we can have milestone for a new generation of smart electromechanical systems based on chain memory alloys. And thank you very much for your attention.